National Data Archive on Child Abuse and Neglect.
Hello, everyone. My name is Noah Wan, and I'm a data analyst here at NDACAN. Would like to welcome you to our first monthly office hours series. If you're new to our monthly office hours series, it's a series we hold every year. With this year, with including the addition of a R training portion. Um, for the first 30 minutes, Frank Edwards will be leading the R training portion, followed by 30 minutes of our typical office hours. From there, we'll be splitting into break rooms guided by three NDACAN members based on admin or survey data sets or career development. If you have any questions, please put them in the Q&A box, or you can come off mute and ask the question, but please do not type your question in the chat for recording purposes. The session will be recorded and all materials will be available on the NDACAN website. Without further delay, I'll kick it over to Frank to start the R portion of our monthly office hours series.
Thanks, Noah, and good morning, everybody. I am Frank Edwards. I'm a research affiliate with NDACAN, and I'm faculty at Rutgers University in Newark. So today, we're going to cover one of my favorite topics, and that's data visualization. As always, the materials are available to you in the box folder. We are on week 6 today, and we've created fake data sets that mimic the structure of the AFGARS and NIDED data. Again, don't use these for research. These are just for practice, but they do mimic the structure, but don't contain any real data. And we also up there have the script that I'll be using, the R script that I'll be using today for your reference, as well as a homework assignment that you can work on to practice some of the skills we're going to work on today. Copy of the slides and a PDF of the slides is also available in the box folder. So today is data visualization. This, again, it's a topic near and dear to my heart, and it should be the core of your toolkit when you're working with data in R. R, in particular, one of the big upsides for using R is that its data visualization tools are incredibly well developed and almost certainly, I would argue, best in class compared to other statistical software suites. They certainly outpace Stata and others, and outpace Python, I think, generally as well. And the main reason for that is the development of ggplot2, which we're going to cover how to use today. The data for today that I'm going to use for demo is the AFGARS 2018 individual level fake.csv. This is simulated foster care data that follows the AFGARS structure, and it's at the individual level rather than the aggregated level. For the homework, you'll work with the aggregated data as well as the individual data. And just to check, is my audio? Yeah, okay, I can, now the mic light is lighting up. It didn't seem like it was coming through. But okay, so, and if you have questions at any point, feel free to just come off mute and ask your question. I don't mind being interrupted. So first, let's talk about the basic anatomy of setting up a plot in R. Our basic syntax for writing, for developing visuals in R using ggplot, which we've been using tidyverse the whole way through. Anytime you library in the tidyverse suite of packages, you're actually loading, I believe, 10 packages when you pull tidyverse in, and ggplot2 is one of the packages that you pull in when you pull in tidyverse with a library command. Now, in order to create a plot in ggplot, we need 3 ingredients. We need a data object that's going to take the form of a data frame or a tibble. We need aesthetic mappings, and we need graphics to draw. So these are the 3 ingredients. First, we need a source table. Then we need to tell R how to map variables in that table onto particular elements of a data visual. And then we need to tell R what kind of visual to draw. So this will take the form in syntax of a command like the command at the bottom of the slide here. We'll use the ggplot function, and the first argument we give to the ggplot function is the name of our data object. We then put a comma, and we use the AES function inside the ggplot function to specify the aesthetic parameters that we're going to use. So AES here stands for aesthetic, and we're going to tell R how to map our variables in the data frame onto particular features of our visual. So in this case, I'm going to specify one single parameter, that's X, and X is going to handle the horizontal position of the element on the visual, and we'll call it variable name for now. Generally, though, the ggplot function itself will take two main features, the name of the data object, comma, AES to specify our aesthetic parameters, and then within the parentheses of the aesthetic call, we'll name out all of our aesthetic parameters. After I've made my initial call to ggplot, I'm going to connect it. We've looked at piping before in using the tidyverse syntax. ggplot has a similar setup where instead of using the pipe operator, we use a plus to string together different function calls. So after we make our base call to ggplot, data, comma, aesthetics with our variables, we use a plus sign and then specify with a different function the kind of shape we would like ggplot to draw. And these are called geoms using ggplot's vernacular. In this case, I'm calling for a histogram, geom histogram. So we have ggplot plus geom, right? This is going to be the basic structure that all of our calls to ggplot will take. Common aesthetic parameters that we might use depends on whether we're looking at bivariates, univariates, multivariates, right? For univariates, we usually only want one variable and we'll specify it as X. X is variable name. For bivariates, and apologies for the typo, we most commonly might use a X and Y, right? For example, if we're making a scatter plot, we'd need a horizontal position and a vertical position, right? And we can just use commas to separate the aesthetic parameters. If we have a continuous and a categorical, we could imagine setting up AES X equals var1, color equals var2. So we wouldn't necessarily need to use Y for var2. We could use color. We could use shape, size, color, fill, right? So we could say shape equals var2, size equals var2, right? For continuous ranges, if we, for example, are looking at producing a plot with error bars or something like that, we can use xmin, xmax, ymin, or ymax to set our upper and lower bounds for vertical and horizontal plotting. And group can also be useful when we want to plot out, for example, separate lines for different grouping variables within a data set. So for example, imagine we wanted to create a line plot over time. We could imagine X equals time, Y equals the variable that we're looking at. Maybe it's caloric intake per day. And group could be equal to exposure to treatment or control group in an experimental setting. And then we could have separate lines for each group. So that can be incredibly helpful. Common geoms that we'll see are geom histogram. Obviously, we've already looked at that. Geom density to create a density plot. Geom point creates scatter plots. Geom line will create line plots. For bar plots, we'll usually use geom bar or geom col, C-O-L, which stands for column. We'll use geom bar when we have the data at the variable level, but when we've aggregated it up to a count, that is, we have a count of incidences within a category, that maybe we're working from something that already looks like a crosstab, then we'll use geom col instead of geom bar. And we can also use ggplot2 for GIS and for mapping. So if we have, for example, shapefiles, maybe shapefiles we've downloaded from the US Census or somewhere else, we can easily attach those to our data objects and use geom SF to draw maps directly in ggplot. So the sky is really the limit. In ggplot, if you can imagine a data visual, you can almost certainly create it using the tools that we've got available to us. So instead of doing a lot of slides today, we're going to go right over into our studio to start practicing with drawing some plots. And I'm going to walk you through some of the most commonly used visuals that you will see in ggplot that I think will be useful for work with our admin data. All right. This, again, is week6.r. This script is up on the box folder if you would like to pull it in and follow along. Now, in our studio, as always, we have our script over here on my left side. We have my console up here, which is where we're going to see the script executed. And then here today, we're going to have our plots viewer that is going to show us the output that we are creating. I'm going to start off by just running the first 10 lines of code here. And nice tip for working with RStudio, if I put my cursor on line 10, and I'm on a Mac, so if I push Command Option B, it will run all lines of code above line 10. So in this case, it'll run this command library tidyverse to pull in the tidyverse packages. And there's ggplot2 that we're working with today. It'll then read in my AFGAR's individual level. And anytime I read in a file, I like to take a look at it. And I used head to do that here just to see the variables that I've pulled in and make sure that everything loaded in appropriately. Let's start with some univariate visuals. I'm on lines 11 to 15 right now. Again, what we want to do are data. We need those three ingredients. We need the data, we need the aesthetic mappings, and we need the geom. So the data we're working with is called AFGAR's end. And then for my aesthetic mappings here, I'd like to look at the age at which a child was first removed from their home and placed into foster care. And we don't see it over here. I'm going to make my text a little smaller for a second so we can actually just see that variable for a second. Got to go very small, or I could make my screen a bit larger. Let's do that. Okay, yeah, here's the age at first rem variable over here. And we can see that this is an integer that takes on values that represent the numeric age of the child when they were first removed into foster care. So we're going to look at the distribution of that variable across cases. Anytime we have a continuous variable so if we have a continuous numeric variable that's observed across a lot of cases, a histogram is a really great way to get a sense of the distribution of that variable. So here's our histogram. This is a great way to get a quick sense of what's going on in the data. So on the y-axis here, we have count. On the x-axis, we have the numeric age, where the height of the bar represents the number of cases that fall into each age integer. So we can see that the most common value for age in the data is 0 and 1. 1 is where the spike is. We also have a lot of zeros. After age 1, we see decreasing numbers going on up to age 17. Now, maybe we want to look at this not as a discrete plot. A histogram will show us the counts on the y-axis, but it doesn't show us the proportion of the data. Maybe we want to know the relative share of the data. We're not so interested in counts. And maybe we have, in this case, we do have a kind of discrete structure to the data because age is represented as an integer, but perhaps we had a more truly continuous variable. A geom density, a density plot, will provide similar information as a histogram, right? It'll give us a quick glimpse of the overall structure of the data. We can still see those two features that 0 and 1 is really where we see most of the children entering foster care for the first time. But now we have a sort of different feature of the data. A density plot can be read similar to a probability distribution in that the area under the curve of this density must equal 1. So we can read this as if we took for example, drawing a line at age equals 1 or 2, we could then kind of imagine what the area under this zone of the curve is to get a sense of what proportion of the data falls in that range. So histograms and densities show us really similar sets of information, depending on how you want to look at it. Maybe we want to look at the distribution of a categorical variable in the data. Here, let's look at the race ethnicity. Okay, something weird is going on here. Let's go back to head and think about what might be happening. Race ethnicity, we can see, is represented here as a numeric. And so when I asked R to give me a geom bar for race ethnicity here, it did that, but it treated it as a numeric variable. When what we might be more interested in thinking about is race and ethnicity as a categorical variable rather than as a truly numeric variable. In order to force R to handle this as a categorical variable, I'm just going to put a factor wrapper around race ethnicity. I don't need to transform this prior to the plot. I can do it within the call to ggplot itself. And that'll give me this visual. This is much more useful. Now I can, at a glance, if I have my code book in hand, tell what the distribution of race ethnicity is across the data set I'm looking at. Maybe I'm interested in thinking about the two variables together. So maybe I want to think about how the distribution of age at first removal differs across racial and ethnic groups. To do that, I can start to add color and other elements to the plot. We're going to start with a simpler one. We're going to start with sex, which takes on 3 values in this data set. It takes on 1, 2, and 99 for missing. The way we can specify this is we can, before we were just using X, we're going to add color now. So I'm going to set X again at age at first removal, and I'm going to set color at factor of sex. Again, sex, like race here, is coded numerically, and we need to tell R that we want to handle it categorically rather than numerically. Let's take a look at what we get. Okay, so now we have 3 density plots. We have the salmon colored line for factor sex is 1, the blue line for factor sex is 2, and then this gray line for the missing values, which we don't have a lot of. There are not very many missing cases in this data. But again, a density plot will show it to us as the proportion of the data, so it may not be as informative as a histogram might be in this case. But let's take a look at this a little differently. We have some trouble here teasing out the difference between the salmon line and the blue line, the pink and the blue line. They really do overlap quite a lot, and so we can't really see them separately. If I am in a situation where I'd like to draw multiple lines, but I don't necessarily want them to all be within the same pane of the plot, I can use this additional function called facet grid, and then I can tell R to facet the plot by sex. The tilde tells it which variable to use for faceting. Faceting is going to produce a series of what are called small multiple plots. It'll produce lots of different versions of the same plot for each value of the categorical that I provide. In this case, I will now get 1 density plot for each value of sex. And this allows us to see side by side each of those values if we don't want them overlaid on top of each other. Now, maybe we want to think about pivoting over to race ethnicity again. This is the density plot when we add race ethnicity as a color aesthetic. And here we can compare these quite nicely. We can see that there are clear differences across groups in terms of the age distribution for the race ethnicity values, but we might want to go back and keep in mind what we saw here on our plot on line 21, this plot, that we have very different amounts of data. For groups 1, 2, and 7, we have the most data. So those might be the ones we want to pay most attention to as we look at the plot. So we have pink, orange, and purple. And the pink, orange, purple, those are the ones up top here. We can see that those distributions look like they do have some slight differences in the proportion of 1-year-olds that are the proportion of 1-year children whose first entry was 1-year-old. Might be something for us to look at a bit more closely. Maybe we want to look at both race, ethnicity, and sex. So here we treated race ethnicity as our color parameter. There's no reason we can't combine both the color parameter with a facet wrap. So we can look now at 1, 2, 3 variables simultaneously. We didn't have enough data in the NA to represent. You can see here this non-missing arguments. So we didn't have enough information. I think we only had 2 missing sex cases, so those just get dropped from the plotting. But now we have a separate density plot for each racial and ethnic group by sex. We could also flip this to make sex, color, and race ethnicity the facet. That would be just as simple as changing around the position of these variable names. Any questions so far? All right, then let's pivot over to scatter plots. Let's look at the joint distribution of age at first and last removal. So here we're going to have on the x-axis the age when the child was first removed into foster care, and on the y-axis the age they were at their last removal into foster care. And of course, for a lot of children, these will be the same if they only have one entry, right? Then x and y will be equal to each other. Let's take a look at what this looks like, though. Okay, that's kind of funky. We actually have a problem here, right? These are our codes for missing data. And I believe here they take on values of 98 or 99. And so we want to go ahead and pull those out. That really throws off our ability to look at this visual. Here, I know that no one over the age of 25 should be in the data. They certainly are not entering foster care for the first time at age 25, and their last removal can't be that age either. So I'm just going to remove all observations that are over 25, and I'm going to use filter to tell R to only retain those values where the age at first and last removal are less than 25. And let's take a look at the plot now. Okay, so this is starting to look a little better, but there's still a few things that are difficult about this plot. We don't know how much data is at each of these points, right? So for age 0, we have observations where the first and last entry were both at 0, but we also have observations at 1, 2, 3, all the way up to 17, right? That is, we have observations at all possible ages, but we don't know how many observations from this visual because all those points are overlapping with each other. So the first thing we want to do is add a little bit of random noise onto each of those points. We can do that in our geomPoint function by adding an argument for position. And we're going to tell R to use jitter to add a small amount of random noise to the position of each plot so that the points are no longer exactly overlapping. Let's see what that looks like. Here we go. Okay, so now the points have all been slightly spread out. And effectively, the areas of the plot that we see that are darker now have more data, and the areas that are a little more sparse, where we can see some gray shining through, those have a little less data. But again, we still have a ton of overlapping data here. So maybe I want to go a step further. I also might want to adjust the transparency of the points. So to do that, I'm going to use the alpha parameter. Alpha takes on values between 0 and 1. And here I'm going to use a 0.25. 0 means fully transparent. 1 means fully opaque. 0.25 will give me a fairly transparent point. Now we can really start to see the density of the data a little more clearly. Most of the data is falling along the y equals x line, right? That's the most, not most of the data, but that's our modal kind of value, right? Is the y equals x line. That is, age at first removal is equal to age at last removal, where we can see a kind of decrease in the proportion of cases that are very far away from y equals x, but there are still some, of course. This gives us a better sense of the exact location. So maybe let's clean it up a little. This is starting to look a little better. And if I wanted to present this in a paper, I would think that I'm getting close, but my axis labels are not particularly useful. To get those ready for print, I'm going to use the labs argument. Labs allows me to set the labels for the different features of the plot, or the labs function. So I'll just plus labs. Here's my x-axis title. Here's my y-axis title. Let's run that and see what we get. Now we have much nicer axis labels. Maybe I decide I don't like that gray background. ggplot has a number of themes that we can switch. Theme minimal is one I often like to use, and we can just add that as a function call after our labs to remove that gray plotting background. Now I have a much more minimal plot. Still has the grid lines. Maybe I want to remove those too. I could continue down that road if I like. Okay, so we've done a pretty good job producing this. Once we've got this plot, we might want to think about whether this differs across racial and ethnic groups, whether this basic pattern is the same across groups. We can facet wrap by race to produce one version of this plot for each group, if we like. Maybe we want to look at child sex. There's no reason we can't take our basic plot here, copy paste it, and then add a color argument. Now we have color. Okay, but again, we didn't factor it first. So we have this treated as continuous, which is a little funky. We're going to switch it over to factor. Now we have the pinks and the blues. And let's clean up that legend. I can adjust that with labs. Color equals sex. I have an error in my code somewhere. I think it's right there. Okay, well, I need to debug this. My apologies. That works. Okay. We could also look at placement setting by sex and by age, right? Here, we're going to look at X as a factor for placement setting. We can make sex color and keep placement setting as X. In this case, though, I might really want to use fill rather than color. Color is going to give us the outline. Fill is going to color the interior of the bar. And I don't want a stacked bar plot here. I really want them side by side. And just like we did position jitter, I can do position dodge to force the bars to be next to each other. And maybe I want to add age at last removal to think about whether differences in placement setting by the age at which the child was removed. Now this plot's getting a bit big. I'm going to need to adjust my window to see it. And here we'll notice that the y-axis, because we know we have more 0 and 1-year-olds in the data, the y-axis is scaled to be constant across groups. Maybe I don't want that. Maybe I'd like to have each group have its own y-axis. To do that, I can add the scales equals free y argument. And now I'll end up with a separate y-axis for each group. Just make sure that your readers are aware that you've done that. And let's get it ready for presentation by cleaning up my labels. Y, X, fill. I can also use title and subtitle to add additional annotations. So this is a pretty close to print ready visual. That's all I've got for us today. Homework will have you work through how doing a few of these exercises with more of the AFCARS individual and AFCARS aggregated data. Does anybody have any questions? Okay. Thank you all for joining us today.
The National Data Archive on Child Abuse and Neglect is a joint project of Duke University, Cornell University, University of California, San Francisco, and Mathematica. Funding for NDACAN is provided by the Children's Bureau, an office of the Administration for Children and Families.